Now we're in part B and we are considering rolling. Still there's no drag. And once again, we will do a similar setup. We will start with the conservation of energy. So we write the equation first. Delta K plus delta KR plus delta UG plus delta UE plus delta I equals to Q plus W. Once again, we will get rid of some of the things. Translational kinetic is there. Now there's rotational one as well. And there's a change in elevation. So, but there's no spring-like objects. We will get rid of that. There's no friction that causes, or there's no kinetic friction, I should say. And there's no temperature or pressure changes. So delta I is still 0. Okay. And heat is going to be 0 as well. And we will look into the work done more specifically by drawing a free body diagram. So one thing, a quick note here, if this is not clear why this is delta I is 0, there is friction, right? In order to roll the ball, you need some grab, and you can see the free body diagram, we have some friction. This delta I is gonna split into kind of delta I just for any temperature pressure changes, and also delta IF. Remember what this was. This is the kinetic friction. Okay, why is that? Because this comes from the work done by the friction, and static friction does not do work. It's static. It doesn't move, right? So there's no displacement, but only the kinetic friction will do work. So if you have kinetic friction, then you need to include it. But since we don't have kinetic friction, that kind of brings me to my free body diagram now. We have again normal force, weight force, and friction force. And first of all, it is up the incline so that it kind of pulls the object that way, so the object rolls that way, right? So that there's rolling. So it kind of grabs the object. But this force is not kinetic friction. This is specifically static friction, because this point, the bottom, the point of the object on the object that touches the ground, only touches the ground once, and it does not slide, so it doesn't move relative to ground. Okay, another point will touch the ground, but it's not, that point is not moving relative to ground either. Okay, so that is the reason this is a static friction, and static friction do not do work. Okay, so from this we got this simplification. We ended up with 4 terms. Now looking at the free body diagram, we can say the same stuff with for the normal force and the weight force. Normal force do not do work. Weight force is already included as delta UG, and static friction also does not do work, right? Because it's static, there's no displacement. Again, these are all explained here. But so what we have is then from here to there, we get rid of the work term as well. Okay, I hope that's clear. And now we're going to expand. So each, since these are change in energy terms, let's expand them. Each will have final and initial. So translational, rotational, and the gravitational potential energies. And we are going to simplify one more time. Initially, there's no motion, there's no linear motion, there's no rotational motion, and final, we set that to be 0 level just like before, so that goes to 0 as well. Okay, so we have only 3 terms left. So from here we get kinetic translational final plus kinetic rotational final and minus gravitational potential initial, and you can put this on the other side, and that's what you're gonna get then. Next thing is to just write those definitions of those energies. Okay, and again, we are dealing with a rigid body, not a point particle, so we need to think about center of mass. So for the translational kinetic, we are gonna say 1/2 mv squared, but v is for the center of mass. And rotational 1/2 I omega squared, I is for the center of mass. And potential energy is mg h, right? As usual, now we've done several examples. So the way to make these two look the same is to use the definition, right? The relation between them. You can either substitute V center of mass with the omega, or write omega in terms of V center of mass and then substitute that in here. And that's what we are doing. So that it looked like we had two velocities, but now you can see that we have only one, and we are going to solve for that. So that's why we wanted to use the second relation instead of the first one, right? So we wanted to get rid of the angular velocity instead of the linear, because we are trying to solve for the linear velocity. Okay, so rearranging this equation, so I would first put those V center of mass together. Pushing the wrong one. So there's V center of mass here, and there's another one here. So put these together, right? Take the coefficients. So the coefficients will be 1/2 in parentheses m plus I center of mass over r square. And you can put the 1/2 on the other side. So it becomes 2mgh, as you can see it here. And at the bottom, the sum of the coefficient of V center of mass square is m plus I center of mass over r square. Okay, so that's, and then take the root because it was squared. Then you're gonna get the definition for V center of mass. Again, this is a symbolic problem, but let's just now kind of look into some specifics. First of all, how can I make this equation look like the first problem, first part? In the first part, there was no rolling, right? That means we didn't have to worry about moment of inertia. So if you set the moment of inertia to 0, as it says here, what do you get? Mass will go away, and then you will have in the root 2gh, okay? And 2 comes out as 1.41, and then square root of gh is the same answer as part A, as it should be, right? So this is a nice check if you did this right, correctly. So kind of a double checking. Another thing that we should see here is that if we have more inertia, moment of inertia, the velocity, center of mass velocity, will decrease, because more the inertia. So if you think about the energy terms, kinetic energy for rotational case is 1/2 I omega squared, right? So if you increase I here, what happens to the kinetic energy? It's gonna go up as well. Okay, so that means initially you had potential energy, and you're gonna use more of that for rotational now. Okay, and less will be used for translational, because you have the same amount of potential. That means you will end up with less velocity. Okay, so that's why the final velocity will decrease in that case. So to see that, we can look into different shapes. So we didn't really specify what type of object we were dealing with. So if we have a solid sphere, now we can write this equation in more detail, and we can get a similar way, like a coefficient of root gh, and we can compare it with part A. Okay, so what we need is the center of mass form. So if we have a solid sphere, you can find the center of mass inertia from the table 10.2 as 2/5 mr squared. Okay, and plug this in to the center of mass here, and then you can get the center of mass velocity, some algebra here, 10/7 gh, and 10/7 comes out as 1.195. okay, in the part A, this coefficient was 1.41, so it goes only 84% as fast with rolling. Okay, so when this 2 comes out, the coefficient of root gh was 1.41. So we can simply compare those now. Okay, so as you can see, since there was rolling, and we used some of the potential energy, initial potential energy, also for rolling or rotational kinetic energy, this translational kinetic energy, or the translational velocity, dropped down compared to part A. Hopefully that's clear. Now if you look at the different shapes, so instead of a solid sphere, what about if we like go a disc of solid disk, for example. Okay, then again from table 10 you would choose the center of mass inertia, 1/2 mr squared, and plug that into the above equation for center of mass velocity. Then you're getting a different coefficient of GH, as you can see, for third, and it comes out as 1/16, and you can see that it is less than the sphere. And again, it really depends on the inertias, okay? And try more, think about a hoop. Again, now we have the inertia of the hoop as mr squared. Now you get GH. It's even less, okay? So now in this case, in 40% lower velocity. So the answers seem reasonable because we were thinking about getting less velocity when there was rolling, and we did that. We found that. And without friction, all sliding objects will reach the same speed at the bottom regardless of their mass or shape. When rolling occurs, the mass and mass distribution have a big effect, okay? And it depends on the shape. So you gotta choose the correct form of moment of inertia from the table 10.2. Again, that table will be also given to you in the exam, so you will see it on the exam page, co-exam page. So you don't need to memorize any of those, you just need to understand how to pick them. And if you have any questions, please stop by in our Zoom meeting so that we can clear things up. After this, there are several questions. They're really good questions. So you're going to answer those as a quiz. And I have added 5 more problems for you to solve. I also have the PDF solutions on the page, class page. So please work on these on Friday and also during the weekend so that chapter 10 is clear. Including the problems, homework problems, please try to do most of them. Again, homework is due Tuesday. And on Monday, I will start with the angular momentum, and we're going to talk about some of those. And these are really cool stuff. And then I'll try to add some videos, some fun videos that kind of comes from these applications of these, okay? Okay, that's all for today. Please solve those 5 problems. I will also, again, add those solutions. Also, the Indiana Jones problems, the solution is also available. And have a nice weekend. Please do your best. We only have a couple days left, and hang in there and take care of yourself.